Hi guys, welcome back. Dr. Mandis here. Today we're talking about Lewis structures and covalent bonding. Last video I left off quite abruptly saying, hey, that was it. And say, yeah, that was it. Now we're going to move into expanded octets. Expanded octets are going to be things that are not obeying the octet rule. Aside from hydrogen and maybe boron, okay? Boron is kind of unique. He has 3 electrons in the p's. I know he looks like he has 2 in the s and 1 in the p's, but what he does is he promotes the 3 up into the p's and leaves the s empty. Leave that be for a minute, okay? If you look at nonmetals, okay, going down that way, nonmetals that have access to d orbitals, okay, d orbitals, okay, that means things that are in the third valence energy or later. So even if you have like the 3s orbitals, 3p, up here just a little bit higher up are the 3d. So in the third energy level, there are more than just 4 orbitals. 4 orbitals are only 8 electrons. We can expand beyond 8 electrons because we can use some of the d orbitals. That's what I mean by expanded octets. Things of the second energy level, C, N, O, and F, these guys cannot expand their octets because there are no such things as 2d orbitals. There's no second energy level d sublevel. That does not exist. So therefore they are constrained to an octet. S and P with 1, 2, 3, 4 pairs. 4 times 2 is 8. 8 makes the octet. Expand that octet by using d orbitals and we can get into some other funky structures. Those structures can be seen here in this tiny little bit table. Another table is busy, but it really depends upon whether they expand by adding 1 more electron pair and making 5, or option B, they expand and make with 2 electron pairs for 6. Okay, so you really got to ask yourself whether we have 5 pairs of electrons around the central atom or 6, because that's going to dictate whether we get into different geometries, whether we're octahedral, square pyramid, square planar, or option B, that for trigonal pyramidal, bipyramidal, seesaw, T-shaped, and linear. Alrighty, if you're coming out of first year high school chemistry, especially if you're one of my students, I often leave off the words trigonal for trigonal pyramidal, trigonal planar, because we all obey the octet rule. If you're into first year college chemistry, AP chemistry, now we're expanding octets. You have different types of pyramidal structures, so you can't just say pyramidal, trigonal, bipyramidal, square pyramidal. Okay, it's not you have trigonal planar for the octet rule, square planar for the expanded octets. So you need to use all the words. You can't shorten them with just one word. Use all of them. Alrighty. The bond angles are kind of, I don't know if they're kind of obvious from the geometry. Just look at whether it's straight, okay, whether it's split into thirds, 360 degrees divided by 3 is 120, or whether you got a bunch of right angles in there. Alrighty. Hybridizations we're going to talk about in a different video because they're a little bit more lengthy. Okay. But as far as the expanded octets, I thought the best way to do it would just be to do some examples. The way you do expanded octets is via the valence methodology where you have to add up the electron pairs and keep track of your valence electrons. You really do need to keep track of valence electrons because you don't really need to know if you have expanded octets or not unless you know the exact number of valence electrons you're dealing with. So let's look at the examples of IF5 and SF4. Our total valence electrons, I is 7 and F is 7. Remember, how do you get valence electrons? You count. Okay? If iodine is here, that's 1, 2, 3, 4, 5, 6, 7. 7 valence electrons for the 4s and the 4p. You do not count the intervening d electrons because they are not valence. They're in the 3d. The 3D, that's one energy level down, so they're not valence. So really just count the S and P. 1, 2, 3, 4, 5, 6, 7, you're good to go. So we had 7 electrons for I and F, 6 for S, and 7 for F again. Do the math. Iodine is 7 plus 5F, so you get to 42 electrons for 21 pairs, 17 pairs for SF4. Remember, the next thing we want to do is bond to the central atom. All right, the central atom is the least electronegative, which in this case, remember, electronegativity increases over and up. For iodine, we got iodine down here, F up there. So Iodine is less electronegative. Between sulfur and fluorine, sulfur is down here, F is up there. All right. Typically, you can also just kind of look at it from the chemical formula of what's what. Okay. So anywho, we got a bond to the central atom. Let's just look at that. If we make singular bonds to the central atom, for the iodine, we're going to use 5 pairs to do that. Okay, so 21 minus 5 makes 16 pairs left. For the sulfur, we're going to use 4 pairs to connect the 4 fluorines for 13 pairs left. Well, then we need to complete those octets. Okay, complete the octets on everybody that's not the center. And so if you look at fluorine, he's got 1 pair of electrons. The red line represents the shared pair. So each fluorine has 1 pair. 4 take away 1 pair. Each fluorine needs 3 more. Okay, so we're going to put 3 electron pairs on each fluorine. Okay, I do those with straight lines. Okay, I tend to use just straight lines all the time. I learned that from Dr. von Frankenberg at University of Delaware years ago. It's just a nice, faster way to do it. It's very non-standard. Most people just use 2 dots. Okay, but I use a straight line because it's fast and easy. All right, and then you get used to the idea. A straight line is a pair of electrons. Between 2 atoms, it's shared. Outside of 2 atoms, it's unshared. So anyway, those little red lines represent the 15 pairs of electrons needed to stabilize the fluorines with an octet. Okay, that means we got 1 pair remaining. And for the sulfur, we use 12 pairs total and have 1 pair left. So in both cases, we have 1 pair remaining that we have to account for. Okay, so where we're going to do that, where we're going to put it on the central atom. Okay, typically your third step, you're either going to complete octets in the central atom by sharing. In this case, we don't need to do that. All right, they're already at octets of 4 or beyond that, like iodine already has 5 pairs around it. But we have extra electrons, so our extra electrons are going to go on the central atom. And we do that. In this case, I do it as a set of dots because it gets really confusing otherwise. And those are my little set of dots that I have right here on iodine, okay, and right here on sulfur, okay. Up above here, initially we just put them on the central atom. We just put it on the central atom. Okay, how do you know how to draw the structure is usually what students then ask. Well, that looks really gorgeous. That's awesome. How do I know to draw that? It depends upon the number of pairs of atoms. You really got to count. For the iodine, there are 6 pairs. For the sulfur, there are 5 pairs. If there are 6 pairs, the pairs go axial. That's the up and down. Okay. If there are 5 pairs, the pairs go equatorial, and equatorial go around the middle. It's just like the Earth, around the middle versus the axis. Okay, so 6 pairs axial, 5 pairs equatorial, and you can draw a beautiful structure that way. The geometry is, if you go to the LAX, if you just look at that previous table, LAX4 is a square pyramid, and if we kind of look at that, it should look like kind of like a pyramid. Maybe I can draw that. You go ink, dink, dink, dink. And so it looks like you got a kind of square on the bottom of a pyramid. This little thing here is called a seesaw. And if you draw it sideways so it looks like this, looks like a little seesaw with kids on it. Okay. Don't get that confused with T-shape. A lot of student T-shape looks like this with 2 lone pairs. Kids call that a seesaw. T-shape looks like a T. Alrighty. Well, those are expanded octets. You really just must get this table down into your belly and get those underway. I'm Dr. Mandis. Have a good time. I'll talk to you later.